last time we started talking about conservation of mechanical energy. And we started by talking about the idea of work. Anyone remember what the definition of work is? Not the mathematical one, but what is work? So work is a change in an object's energy caused by the application of a force. And so if F is the force vector acting on an object, and lowercase d is the displacement of the object, then the work done by that force on the object is the x component of the force times the x component of the displacement plus the product of the y component of the force times the y component of the displacement. So as a consequence, so this is how you calculate the work. As a consequence, so first of all, what if you apply a 10 billion ton force to something that doesn't move? Well, that thing would have to be anchored pretty well, but say that that happens, okay? What's the work done by a 10 billion ton force pressing against something that doesn't move? Zero, yep. So objects have to move. So, sorry, let me reword that. So a force only does work if the object moves. Second, this is a little harder to see from this equation, but if the force vector and the displacement vector, let's say the force vector and the motion, are about in the same direction, work is positive. Okay, so intuitively, we're going to think of an object's energy as its speed, okay? I mean, it also depends on its mass, but the object's mass never changes. So to increase an object's energy, you increase its speed. To decrease its energy, you decrease its speed for now. So if you apply a force in the direction it's going, you speed it up, you increase its energy. So that sort of makes sense, right? What if the force and the motion are roughly in opposite directions? What would you expect to happen? Well, physically, what happens is it's coming this way. You apply a force in the opposite direction that slows it down. So the energy goes down, the speed goes down, and that is a negative work. Okay. And that just comes out of that equation. You could try plugging some things in and you'd see how it works. The cutoff is whether those two things are within 90 degrees or more than 90 degrees apart. Okay. So if the force vector and the motion are in, sort of in the opposite direction, within 90 degrees of being in the opposite direction, then work is negative. Positive work means you're increasing the object's energy, and negative work means you're decreasing the object's energy. And then the last thing, this is going to be a surprisingly important fact. Well, what if they're exactly 90 degrees apart? I said that was the cutoff. So what if the force vector and motion are exactly 90 degrees apart? Then the work is equal to 0. Um, okay, and then after that, I talked about, I think I just introduced the idea of conservative and non-conservative forces. Um, conservative forces are those where if you know the object's location, that's enough to specify the force. It doesn't matter where the object's gone before that, okay? It's independent of the path that the object takes to get there. If you know that the object is in this spot, there's only one force that can be applied to it. So a conservative force is one where knowing the object's location is enough to know the force. We have two examples of that in this class. Anyone remember what they are? Exactly. So there's the weight force, and that one's even, so whether something's a conservative force or not just is determined by whether its location is enough to specify the force. Weight, you don't even have to know the location. You just know that the force is mg down no matter where it is. Spring force is one we haven't thought about yet. But the idea of a spring force is if the spring is stretched a certain amount, it applies a certain force. If it's compressed a certain amount, it applies a certain force. And it doesn't matter what you've done to get there. You could stretch it out to here and then come back to that spot, compress it and come to that spot. Either way, if you get that spring to a certain length, faced in a certain direction, it's going to apply a known force. Okay, so that's the idea. Non-conservative forces for us, well, let me say a little more about this. So there are other examples of conservative forces. Magnetic fields are a conservative force, electric fields. We're just not going to do any problems with those. But the big picture idea is a conservative force is one that has, and you've heard this word on Super Friends or whatever, a force field. That's those those two phrases mean the same thing: conservative force and force field. What a force field, the idea of a force field is wherever you go, you can imagine that there's a force there waiting for that object. Okay. And it doesn't matter where you go to get there. If you get to this spot, that's the force, the one that's waiting there for you. It's like if there's a field of daisies, everywhere you go, there's a daisy there. Ah, so nice. In a force field, you go there and there's a force. It might not be as nice. So weight is applied by a force field. You can think of it that way. Um, you can imagine there's just these vectors with a magnitude mg waiting at every location. And when you get to that location, that force is waiting to pull you down to the ground. And it's the same thing with the spring. You can imagine that as you imagine this spring attached to the wall. If you stretch it out, you imagine that wherever you pull this object to, there's a force waiting at that location with a known value and direction, ready to pull it back or push it back or whatever. So force fields aren't as interesting as in superhero shows and stuff. They're just like gravity is a force field. You know, like they're always like this cool power. Well, gravity is a force field. So we all have the power of force fields, but not very strong. Okay, so non-conservative forces is everything else. Um, and the requirement there is that at a single location, the force vector could take multiple values. What? Okay, well, depending on just the circumstances. Um, so I think this is what I did last time. So an easy one to think of is friction. So we know that if we have the mass of this thing, uh, there's like a weight force vector waiting in space, and you put the thing at that location, and the weight pulls it down with that value. And it doesn't matter how you get there. If I do this a bunch of times and then put it there, it still has the same direction and magnitude as if I get it there like this. So now let's think of friction and compare to the idea of a conservative force. So let's say this is the location, okay? And I'm going to get to that location two different ways. The first one, I'm going to slide it like this, okay? Well, if I'm sliding it that way, the friction force vector is this way, okay? And so when it gets to this location, there's a friction force in this direction. Now I'm going to do it from the other side. If I slide it like this, the friction force is that way. And so at this location, in two different cases, the direction of the force is opposite, okay? So it wasn't enough to specify this location to know what the force is, okay? A normal force, so say that's the location. The normal force is one thing right now. If I push down on it, now the normal force is bigger, and it's still at the same location. So that can't be a conservative force. Okay. But practically speaking, in this class and in most, maybe all problems that you'll see in physics, the way to think of whether something's conservative or non-conservative is it weight or a spring force? If it is, it's conservative. If it's not, then it's non-conservative, most likely. Okay, so what is useful about, like, why would you make this distinction? So we split forces into conservative and non-conservative because it happens to be easy to calculate the work done by non-conservative forces. No, easy to calculate the work done by conservative forces. Okay, and here's why that is. For conservative forces only, there's something called potential energy. And this potential energy is related to the work by the relationship work is equal to the negative change in potential energy. Okay, so this potential energy depends only on the object's location. And if you calculate the potential energy at one instant and then at another instant, you can use that to calculate the work without, the calculation of work can be sort of complicated. So this makes it easy. So here are, in order to do this, you need to know what the mathematical functions are for the potential energy. So here are the potential energy functions for weight and spring forces. So first, for the weight, the potential energy, gravitational, is equal to the mass of the object times positive 9.81 times the height. Okay, so this is the object's mass. G is positive 9.81 meters per second squared. And h is the object's height. That means that any object's potential energy increases as it goes up and decreases as it goes down. And then for spring forces, the potential energy for the spring, for the force applied by the spring, is 1/2 times this constant K that represents how stiff the spring is, times x squared. Write down what these mean. Um, K is called the spring stiffness. So if you have a spring that's really hard to stretch, that has a big value. If you have a spring that's really flimsy, easy to stretch, it has a small value. And this X is the distance that the spring is stretched or compressed from its resting length. Um, okay, so what this means, so notice, having a potential energy function means that the work done by a conservative force um, from, let's call it an instant one and an instant two. So force, the work done by the conservative force from instant one to instant two can be calculated from the object's location or locations at instant one and instant two. Okay, so for conservative forces, that's weight force and spring force. If you know, if you want to figure out how much work spring or weight has done as this object, over half an hour as this object does all these things, okay? All you have to know is the object's location at the start of the half hour and its location at the end of the half hour, and you can use these functions to calculate it, okay? Generally speaking, for non-conservative forces, calculating the work is a lot harder than that, okay? So for non-conservative forces, it's a lot more complicated. We're not going to get into how to do it. Um, but there are two cases that are going to come up often where non-conservative forces, and these actually, we're lucky with this, certain kinds of non-conservative forces do zero work. Um, so there are two important non-conservative forces that do zero. Um, the first one is a normal force in a rolling or sliding uh, problem. And the second one is any force that points toward the center of a circular motion. People call that a centripetal force. It's just so if there's a circular motion and you have a force that points toward the center of that circular motion, it does no work, no matter what the force is. So any force acting toward the center of the circular motion. The big result. And this is conservation of mechanical energy. If the only forces that do work on an object from instant 1 to instant 2, instant 1 to instant 2 are conservative, then if you add up the kinetic energy at instant 1, we'll get some practice with it. But anyways, this is the kinetic energy plus the potential energy at instant 1. That has to be equal to the sum of the kinetic energy plus the potential energy at instant 2. So notice what this lets you calculate is a relationship between an object's position in only some cases, but if your only non-conservative forces are the things with zero that do zero work, normal forces and centripetal forces. And then all the other forces are conservative, so either the weight or the spring force. Then you can calculate a relationship between the object's speed and its location. And a lot of times that's useful, Sometimes we want other relationships and this wouldn't work, but if you're looking for a relationship between, so this object starts out here with this speed, what's its speed going to be when it's over here? Then this will do it in a really simple way. So practically speaking, you can think of it this way. If the only forces are weight, spring, normal, and centripetal, then you can use that equation. So 1/2 m times speed squared plus the total potential energy at instant 1 is equal to 1/2 mv squared plus the potential energy at instant 2. This expression, 1/2 mv squared, is called the kinetic energy. And it's called conservation of mechanical energy because we're going to call the kinetic energy plus the potential energy, that's what we'll call mechanical energy. And so this says that over time that stays constant. The two can, the potential energy doesn't stay constant and the kinetic energy doesn't stay constant, but the sum of the two of them does. Okay. Yeah, let's do an example and we'll see sort of how this works. So let's say we have this hill. Let's say it's 10 meters high. And someone starts out on skis up at the top. And let's say the mass of this person is 30 kilograms. So let's say that the skier starts at rest at the top of the hill. What's the speed at the bottom of the hill? Okay, so practically speaking, so philosophically, I mean, the idea is we have to figure out what are the conservative and non-conservative forces. Any non-conservative forces, we have to figure out how to calculate them. Practically speaking, though, I mean, we're just looking for like what forces are acting and are there any forces that aren't one of those four, okay? So anything besides weight or a spring force or a normal force in sliding or rolling or a centripetal. So that's the question you have to ask yourself on these problems. In this case, I mean, one thing that, like, if you can't just look at it and tell, it might be helpful to draw a free body diagram of just sort of an arbitrary point along the path. But so what forces are acting on this skier? Draw a free body diagram. Yep. Yep, that's the normal force. Okay, so that's good. So far, there's a normal force. Even though it's non-conservative, it does no work, so we get that for free. That's a good question. We're going to ignore the friction. And if we can't ignore the friction, it gets more complicated. No, wait. Yep, and those are the only two forces acting. Uh, so yeah, we're going to ignore the friction here. So anything besides those four? No, just weight and normal force. Okay, so now I'm going to just set this up. This is always a good way to do it, I think. So I'll break this up into an instant 1 and an instant 2. And for each one of these columns, I'm going to calculate the kinetic and the potential energy. So at instant 1, that's at the top of the hill. The potential energy is just gravitational. There's no spring. And to calculate the gravitational potential energy, that's the mass times 9.81 times the height. So the mass is 30 times 9.81. And now we need the height. And now we have to sort of think about what it means to put the height into this thing. Like, what's the height we're talking about? Are we talking about the height off the ground or the height from the center of the earth? It turns out that as long as you're consistent through the whole problem, you can choose anything to be your zero height. Okay. You just can't change it in the middle of the problem. So we might as well call our height equals 0 the bottom of the hill. I usually just say height equals 0 is like the lowest spot in the problem you're doing. And so at the top of the hill, then, you would be at a height of 10 meters. And if you multiply these out, you get 2943. And since this is SI units, that's in joules. And then the kinetic energy at instant 1, that's 1/2 times the mass times the speed squared. What's the speed squared at the top of the hill? 0, yep. And so there's no kinetic energy. And so now we'll calculate the same things at the bottom of the hill. Potential energy due to gravitation is the mass, 30, times 9.81, times the height. What's the height at the bottom of the hill? 0, because that's what we chose to be our 0 height. And so this is 0. There's no gravitational potential energy at the bottom. And then the kinetic energy is 1/2 times the mass of 30 times the speed squared. What's the speed at the bottom? That's what we're trying to calculate. So we'll just leave that in as a variable. And now conservation of mechanical energy says 2943 plus 0 is equal to 0 plus 1/2 times 30 is 15. So 0 plus 15 v squared. So that is 147.15 equals v squared, I think. And then what's the square root of 147.15? By 15, yeah, did I do that wrong? 196.2. Okay, so square root of 196.2. 14.0 meters per second. Okay, so um, so if you have a hill that's 10 meters high, um, so a little over 30 feet high, and you go straight down with no friction, the speed at the bottom is 14 meters per second, 30 miles per hour, pretty fast. Um, the amazing thing about this is that answer had nothing to do with the shape of the hill. You know, as long as you can get down there, if there's no friction, you could take any path you want, and at the bottom you'd have the same speed if there's no friction. That's a big if, you know. That also, if we set the problem up as there not being a hill at all, and you just calculated how fast this person would be falling at the instant they had fallen straight down 10 meters, it would be the same. It has nothing to do with the path they take. Um, I don't know. That's amazing, right? Like, what if the hill did this, you know, or this, or straight down and then flat? All of those, if there was no friction, when you got to that point, you'd have the same speed. Okay, let's do an example that has a spring in it. So let's say that's the wall, and there's a spring attached to a little cart on wheels. Now, we have to assume, we're assuming that those wheels are frictionless, and we're also assuming that those wheels don't have very much mass, and they're not very big, because that would affect the answers in this problem. What we're really assuming is that this is just like a block sliding along ice, you know. But if these wheels are small enough and light enough, it's basically the same thing. So let's say that this has a mass of 5 kilograms. And let's say that this spring has a spring constant of 400 newtons per meter. That's the units of the spring constant. So let's say that we pull the mass back 8 centimeters from the spring's resting length. And we want to know what's the speed of the cart as it moves past the spring's resting length. Okay. So in this world where there's no friction, um, no air resistance, the spring doesn't heat up at all or anything, so we don't lose any energy. If you pull this back 8 centimeters and let go, it's just going to oscillate back and forth like this. Does that make sense? Anybody have any questions about that? If you pull it out, it's gonna zip this way until it compresses the spring enough that the spring starts pushing it back that way. And it'll push it back and it'll return to 8 centimeters away from the resting length again and just keep going forever with that same magnitude of oscillation. And so if you pull it back 8 centimeters and let it go, it's going to speed up the whole way that it's getting to the spring's resting length. When it's at the spring's resting length, it's going to be at its fastest. And then the spring's going to start slowing it down until it finally turns it around and makes it go back the other way. Okay, so let's calculate that speed. So what's the first step in doing these? Well, the first step is just making sure that the equation that we have applies. So again, think of like a free body diagram. What forces are acting? There's a weight. There's a spring force. And there's a normal force. There's no centripetal force. So that means we can use conservation of mechanical energy. So let's set up this little table. Here's instant 1. Here's instant 2. Okay, so this time we have two types of potential energy. We have gravitational and spring potential energy. At instant 1, let's say that this is the one where it's 8 centimeters away from the resting length. Let's do the weight force potential energy first. So the gravitational potential energy, that's equal to the mass of the cart. What did I say, 5? Times 9.81 times the height of the cart. Well, we get to choose one height. Is the height of the cart going to change at all in this problem? No, so we might as well make our height equal 0, the height that it's at through the whole thing, and then those will just go away. And now the potential energy for the spring, that's 1/2 times the spring constant of 400 times 8 centimeters squared. To put it in SI units, we need to write that as 0.08 squared. It's 0.08 meters. And can someone calculate that number for me? $16? 1.28. And then if we're just pulling it back and letting it go, we're letting it go from rest. So the kinetic energy at that instant is 1/2 times the mass times the speed of 0 squared, so 0. And then at instant 2, the gravitational potential energy is 0 again, because it's still at that height of 0. You can see in this case, I think, why you get to choose what you're going to call h equals 0, and it doesn't change the problem. The only thing that's going to matter is the difference between the gravitational potential energy at instant 1 and instant 2. You know, so what if we had chosen our 0 height to be the center of the Earth? I forget what the radius of the Earth is, but so this is going to be a million or whatever. This is also going to be a million. You'll have one of those on each side of the equation, and they just cancel. Nope, nope, doesn't matter. Okay, and then the potential energy for the spring, that's 1/2 times 400. And then what's the distance at instant 2? What's the distance that the spring is from its resting length? Well, what we want is we want to know how fast it's going at just that one little instant where the spring is at its resting length. So it's going to be 0. And 0 represents the spring being at its resting length. And so the spring potential energy is 0 here. And then the kinetic energy, do we know the speed? That's what we want, so I'll just leave that as v squared. So this is 2.5 v squared. So conservation of mechanical energy says 0 plus 1.28 plus 0 is equal to 0 plus 0 plus 2.5 v squared. And so could someone calculate v? 0.715 meters per second, and we want the positive one. So if the spring was stiffer, what do you think would happen? So now you have a stiffer spring, the coils are thicker metal or whatever. You still pull it back 8 meters, it's harder to do. But what do you think will happen to the speed at the instant that it returns past its resting length? It'll be faster. Yep, the stiffer the spring, the faster it's going. Um, and the flimsier the spring, like if if you attach a spring that is like hanging down, it's so weak, and you stretch it out, it's just barely going to get this 5 kilogram mass moving.